In this video, I want to talk a little bit about probability, and I want to go over some examples that talk about conditional probability. So let's talk about an experiment here. And this experiment is you have a bag of marbles, and in this bag there are 5 green, 4 white, and 3 red marbles, and each of these are labeled. Let's say there's a G1 on the green marble, G2 on the second green marble, G3 on the third green marble, etc. So they're all distinct. And our experiment is we're going to reach your hand in the bag and we're going to choose 2 marbles from the bag at the same time. So it's not like we choose one, look at it, and then put it back and choose another one. No, we choose 2 marbles from the bag at the same time. And we're going to note the colors. So the things that I care about, the events, are going to be keeping track of the number of red marbles that we draw and the number of white marbles that we draw. So let's call the event Ri if we draw I red marbles. So R0 would be drawing no red marbles out of R2. R1 would be drawing 1 red marble, and R2 would be drawing 2 red marbles. And similarly for W, except we're doing it with white marbles instead of red. Okay, so not thinking about the events just yet, let's think about the number of outcomes of this experiment. And let's say it's equally likely that each outcome is picked. See if you can determine the number of outcomes where we have 5 green, 4 white, and 3 red marbles, and we're choosing 2 of them. So pause the video now, have a think, see if you can figure that out. So what is our experiment? Our experiment is we have our 5 green, 4 white, and 3 red marbles, so that's 12 marbles in total. We're picking 2 of them, and we're not picking the other 10. So this is an arrangement problem. Say if we wanted to arrange check marks and X's, every arrangement of 2 check marks and 10 X's will give us a different selection of our marbles. So in total, there are 12 symbols in total. 2 of them are check marks. 10 of them are X's. And let's figure this out, I guess, by hand, because it's quite easy. So it's going to be 12 times 11 times 10 factorial over 2 factorial, which is just 2 times 1, times 10 factorial. And we can cancel off these 10 factorials. And we can factor out a 2 from 12 to get 6. So our final answer is 6 times 11, which is 66. Now you don't need to do that by hand. You could do that using a calculator if you like as well. But we know there are 66 different outcomes to our experiment. So remember, probabilities in general of any event, let's call the event E, if you're dealing with situations where each outcome is equally likely, it's the number of successes, so the number of things satisfying your event, over the total number. And we already know in this situation, the total number of outcomes is going to be 66. And then for each different event, we're going to have to calculate the number of successes there. But we are indeed well on our way. So now I want to figure out all possible probabilities. So I'm going to do it in a 2-way table. So maybe pause the video now and see if you can come up with a 2-way table that gives us every possible combination of the number of reds picked and the number of whites picked in our experiment. You don't need to fill it in just yet, but see if you can come up with the two-way table so that we can indeed fill in the probabilities. So pause the video now and try it yourself. So here's the outline for our two-way table here. All possibilities of choosing reds and white. So everything from no reds, 1 reds, and 2 reds. And with the other direction, choosing 0 whites, 1 white, and 2 white. Now, remember, our experiment is choosing 2 different marbles out of 12. So there's going to be some places where it's just impossible to have both events be true. Let me show you one. There is no way to choose 2 whites and 2 reds at the same time. So we automatically know that the probability of doing that in our experiment is 0. So maybe pause the video now and see if you can fill in the other zeros into this two-way table. Okay, any time where the number of marbles drawn in total exceeds 2, so it's bigger than 2, well, that's just impossible if we're drawing 2 marbles. So we can't both draw 1 white marble and 2 red marbles. That's impossible, so that's a 0. And similarly, we can't draw 2 white marbles and 1 red marble because we're only drawing 2 marbles. So we know the probability of doing that is 0. Remember that the probability of both of these events happening at the same time is what goes in this box. So it's probability, in this case, of drawing no whites and 1 red would go here, for example. So we have 6 different probabilities to figure out. And we know the denominator of all of these guys is going to be 66, since that's the total number of outcomes. So I can just put that in to all of my cells here, and then we can figure out the numerator for all of these guys separately. Okay. So let's start off with this one, drawing no reds and no whites. Well, there's only red, white, and green marbles, and if we have no reds and no whites, we must have all greens. So we must have drawn 2 green of the 5 green that are in there. So we're choosing 2 of the 5 green. So let's say this is cell, I'm going to put a little I here. So cell I, that is, we must be choosing, there's 5 green marbles, and we're choosing 2 and 3 not. So it's going to be 5 factorial over 2 factorial, 3 factorial, and you can check either by your calculator or similarly to what we did by hand in the previous example. When we were figuring out the total number, we should get here 10. So there's 10 successes where we would be drawing no reds and no whites. For example, maybe one of them would be if we drew, for example, G2 and G4 at the same time. That's one outcome that fits into this scenario here. Okay. Let's do one more. Let's do this guy here where we draw 1 red and 0 white. Okay. Let's see if we can work this one out. We'll call this 2. So here we have 2 things going on. So we have 0 whites and 1 red. So if we're drawing 1 red, that means, so let's write that down. So 1 red. And, well, if it's 0 whites, well, it must be 1 green. since it's not red, since we're only drawing one of those, and it's not white, so it must be green. And these are independent. Whatever red marble we draw, it's not going to affect the number of green marbles we can draw. So we know there's three. Let's do the red first. So this will be case A. So there's 3 red marbles. We're drawing 1 and 2 are not. And you don't need to do a calculation here. I think it's pretty easy to see that if you have 3 things and you choose one of them, there's 3 different ways of doing it. But let's do the calculation anyway. So that's 3 factorial over 1 chosen, 2 not chosen, and that does work out to 3. And similarly, for B, where we're choosing 1 green, since, remember, we're choosing no whites and 1 red, so the only thing left over for that other thing is a green. So here we're choosing, again, we have 5 greens. There is 1 chosen and 4 not. And I think it's pretty obvious that this is 5, but if we want to write down the calculation, it's 5 factorial divided by 1 factorial, 4 factorial, and that is 5. But I think everybody just knows that if you have 5 things and you choose one of them, there's 5 different ways of making that choice. So in total for this case, we choose, there are 3 ways of choosing the red marble and 5 ways of choosing the green one. These choices are independent of each other. So there are 15 ways of choosing 1 red and 1 green marble. Great. Okay, so I think as an exercise, it's a good idea to pause the video and see if you can work out the other 4 probabilities here. Just do the same type of reasoning that we did for these 2. That will give you a nice way of doing it. Just think that whenever there's a 0, you're thinking, well, if you're choosing none of that color, the only other color that's left to choose is green. So then you're thinking about that being choosing, the rest being green. So pause the video now and see if you can fill in the rest of these guys. Okay, now that we're back, you should get, in the case where you're choosing 2 reds and no whites, there are 3 different ways of doing that. 0 reds and 1 white is 20. 1 red and 1 white is 12. And 0 reds and 2 whites is 6. So hopefully that makes sense. And let's fill in our total columns here, and then we can start doing some probability calculations. So the probability for drawing exactly 0 reds, irrespective of how many whites you draw, well, what's that going to be? We just need to add these together. So we're going to get 10 plus 20 is 30, plus 6 is 36. So it's 36 out of 66. Probability of drawing 1 red, irrespective of the other marble, is 15 plus 12 is 27 66ths. And the probability of drawing 2 reds is, well, that's just 3 66ths. And let's go across this way. Let's do the probability of drawing exactly 0 whites, irrespective of the color of the other marbles. So that is 25 plus 3 is 28 over 66. Then we have 20 plus 12 is 32 over 66. And finally 6 over 66. And you can check that if we do add 36 plus 27 plus 3, we get 66 over 66, which is 1. That's good. And 28 plus 32 plus 6 is also 66 over 66, which is 1. So we did our little sanity check, and everything makes sense here. Okay, so here is our probability table written again. And let's see if we can do some probability calculations in this. So let's say that we want to figure out the probability of drawing one white marble irrespective of the other marbles. Well, that's easy. We just look in our total column. So here is one white marble. Here are the conditions on how many red marbles we have, but we don't really care about that. So it is just 32 out of 66. So it's the total column for white 1. So the probability that we draw one white marble, and 33 out of 66 is a half. So this is just less than a half. Great. What about the probability that we draw either no white marbles or no red marbles? And remember, you might see the symbol union instead of the word or. They mean the same thing in our case. So pause the video and see if you can figure this probability out. Okay, now that we're back, we can do this in two ways. We can add up all of the cells that have 0 red or 0 white. So it's 1, 2, 3, 4, 5. So it's those guys. Or we can use the fact that it is the probability of drawing 0 white plus the probability of drawing 0 red, but we double counted this AND cell here twice. So we need to subtract off one copy. So let's do that. So the probability of no whites plus the probability of no reds minus the probability that we double counted, which is the probability of no whites and no reds. So that is no whites is 28 out of 36. No reds is 36 out of 66. Sorry, this is 66, not 36. My mistake. And we're subtracting off 10 out of 66. And remember, all probabilities have to be between 0 and 1. So our sanity check at the end of this is to make sure that we have a number that is positive and not bigger than 1. So 28 plus 36, we can check. That is 64. So this is minus 10 is 54 out of 66. Great. Let's do a couple more. Let's do a conditional one here. Let's find the probability that you draw one red marble given that you drew 0 white marbles. So our table is pretty easy to use for this. Remember, we're reducing our sample space just to drawing 0 white marbles. So we're forgetting all of this. And our table is now, for this particular question, just this. So our denominator is going to be that. It's going to be 28 over 66. And our numerator is going to be 1 red. So it is this here, 15 out of 66. Great. And when you're dividing fractions, and these fractions have the same denominator, you can check that these guys just cancel. So it ends up being 15 over 28. And 15 over 30 is a half. So 15 over something smaller is going to be bigger than a half. So this is just bigger than a half. So if you know that none of the marbles are white, the probability that one of them is red is just over a half. Let's do another one here. Let's do the probability that, let's do this one. You draw no white given that you didn't draw no red. So maybe pause the video and see if you can think about how to deal with this one. So we don't have the negation of R0 in our table, but we might be able to build it. Remember, the negation means everything but R0. So pause the video and see if you can figure out how to deal with that. Okay. Well, if it's not R0, it must be R1 or R2. If you didn't draw 0 red, well, your only other options are drawing 1 red or 2 reds. So we're going to, this is the same thing in our case, and it changes depending on the problem. But in our case, this is just the rest. This is either drawing 1 red or drawing 2 reds. So we're reducing our sample space to just these guys here. We're not including the column that has 0 reds. So what's the total probability in this column? Well, it's going to be the sum of R1 and R2. So if we combine these probabilities for this particular question, we are going to get 27 plus 3 is 30 out of 66. So we know that the probability of drawing either 1 red or 2 reds, or put another way, not drawing no reds, is 30 out of 66. So that's going to be in our denominator. That's the total. And what about the numerator? It's drawing 0 whites. So we can either draw 0 whites and 1 red, or 0 whites and 2 reds. So we add these together. These are mutually exclusive, so there's no overlap. We don't need to subtract anything. So we get 15 plus 3 is 18 out of 66. Again, so the number of successes, or the probability of success here, is 18 out of 66, the sum of these guys. And the total probability is 30 out of 66, the sum of these guys. And this simplifies to 18 over 30 when we're dividing fractions with the same denominators. Those denominators cancel. You can multiply by the reciprocal to check that. And we can simplify this if you like. I see a common factor of 6 in these guys. So 18 divided by 6 is 3, and 30 divided by 6 is 5. So the probability, if you didn't draw 0 reds, the probability that you drew 0 whites is 3/5, or 60%, or 0.6, however you want to put it. So you can see, once you have the two-way table here, it's really, really easy to determine a probability. Okay, great. Let's move on from here, and let's fill in one more two-way table. I'll give some information about probabilities and conditional probabilities, and let's see if we can use that to fill in the rest of the table. Okay, so I'm going to do this two-way table a little bit differently. Honestly, it's the exact same in concept as putting the probabilities in your two-way table, but if you want, you can come up with a fictitious population, and then instead of determining probabilities out of 1, you're just determining rates out of whatever size your population is in. So let's say my two-way table looks like this. So we only have two events, A and B. So you're either in A, not in B, or not in B. And again, we have total columns. And maybe I'll draw this out here. But remember, you can view this as a Venn diagram if you like too. So if this is A and this is B. So this region, the intersection, is when you're in both, so that corresponds to this box here. This region where you're in A but not in B, that corresponds to this region where you're in A and not in B. Similarly, this region here corresponds to being in B but not A, so that's that there, that corresponds to that. And then finally, neither being in B nor A, that corresponds to outside of my Venn diagram, so not being in it at all. Okay, but for this purpose, let's put a population in here. So rather than saying that the total is 1, let's say there are 100 people in my population. Then I could work out, let me just erase this Venn diagram here. If I want to, I can work out the number of people in each of these events here. So let's look at the probability of A is 0.3. So if the probability of A is 0.3, and there's 100 people in my population, then I can say that this box here, the total for the probability of A, the number of people, is going to be 0.3 times the population, which is 30 people. So if there's an event A which has a probability of 0.3 of happening, and I have 100 people or 100 objects in my population, I would expect that 30 of those would satisfy being in event A, since it has a probability individually of 0.3. So I would expect 30 in here. And I already know some other information. If this is 30 and my population is 100, if there's 30 in A, there must be 70 not in A, the rest. So 100 minus 30 is 70. Okay, so we used all of this information here. That's great. So let's look at this situation now, the probability of B given A. Remember, this tells me that I'm reducing my sample space just to having A happen. So there's my sample space there. I'm forgetting about all of this stuff. It's just this here where A has happened. So my total population now where A has happened, well, that's just 30. And I know that 40% of these 30 are going to be in B. So I know that probability of B given A is 0.4, but I know that's some number of people that I need to figure out over 30. And if I multiply both sides by 30, I get, well, 0.4 times 30, you can check in your calculator, is 12. So my total population there is 12. And I know if there's 12 people that are in A and B, and there's 30 people in total in A, well, the rest of them must be in A, but not B and B. So I know that total has to be 30, so I know this has to be 18. Okay, great. And I can do this calculation here similarly. The population of not B given not A. Maybe pause the video and see if you can use this last bit of information to fill in the rest of the table here. So give that a go. Pause the video now and try that. Okay, now that we're back, let me erase this stuff just to make a little more room. So we know that if we're in not A, that's these 70 people that aren't in A. So we know that the probability of not B given not A, well, we know that's 30% or 0.3. And that is, well, our total population is 70. And again, we need to figure that out there. And if we do so, we get that 21 equals x, multiplying both sides by 70. So what's that? So these 21 people are here. So these 21 out of these 70 are not in B. That's 30% of them. So the rest must be in A. And how many is that? That is 49. Great. And then we can just total our rows here, since we already totaled our columns. 12 plus 49 is 61. And 18 plus 21 is 39. And we can do a sanity check. 61 plus 39 is indeed 100. So it looks like we did this correctly. Great. So from here, we can do a whole whack of probability calculations if we like, reading them off the table just like we did in our previous examples. And again, if you wanted to use probabilities instead, it would look very similar. This would be, you just divide everything by 100 here. So this would be 1, this would be 0.12, 0.49, 0.61, 0.39, 0.18, 0.21, 0.3, 0.7. So either way you do it, it's all good. In fact, you can either put a population of 1 here and then work out the proportion in each box in terms of the probability, or you can pick a fictitious population of whatever size you like. The reason I picked 100, if you are going to do this and you want to avoid decimals as much as possible, my reasoning here, and if you have nice small tables like this, it usually works. So I notice I have 1 digit past the decimal place to the right, so the 10th place. So I want 1 more 0 than that. So if I have 1 digit here, I want 2 zeros. So if I had, for example, maybe 0.35 here instead of 0.3, then I'm like, oh, I have two digits past the decimal to the right this way, so maybe I want a population of 1,000 instead in this example. But again, you don't have to do that. If you're fine with decimals, that's good to go too. But I just know some people like to think of these more conceptually and like actual objects to deal with. But either way is fine. It's literally doing the same thing. Hopefully you found this video helpful, and we'll do some probability calculations with them next class as well.